Hello everyone, thanks for being here. In this talk, I will show how we predict the number of application US colleges receiving using the college data set and three models, ordinary risk squares, rich, and Lasso. I'll move on from the problem and data to model institution, uh, touch of theory, result on a head-out test set, and finish it with practical takeaways for admissions forecasting. Here's our path for next 20 minutes. I motivate why application prediction matters, introduce the data set and how we split it and outline the three models and what regularization actually does, present OLS, Rich, and Russell results on the test set, connect those results to bias, variance, and cross-validation, and close with implications, trends, and concrete recommendation. Okay, let's move on to number 8. In this exercise, we will predict the number of application received apps using the other variable in college data set. So in my code, I import trains test split, linear models, metrics, NumPy, and load data from ISRP package and the load data set and build predictors and set X and Y and printed Y min and Y standard and learn test set split to create the split we used throughout. So let's move on to the result. We used college data set with 777 institutions. For each college, we observe whether it is private apps of set low academic quality, which are top 10 percentage, top 25 percentage, and blah blah blah. And our response is apps. In this implementation, we exclude the categorical private field and proceed with 16 numerical predictors. We split them 70% and 30% into, which is 547, 43 training and 234 test observations. In the full sample, mean is around 3001.6 and standard deviation is about 3870.2, so counts vary widely. Oh. Ordinary risk squares minimize the sum of squared residual and provides a transparent baseline, but with many or correlated predictors, it can overfit. Rich regression as an R2 penalty that shrinks all coefficients smoothly to 0, establishing estimates without dropping variable. Lasso as an R1 penalty that can drive some coefficient exactly to 0, performing automatic feature selection and yielding a sparser, a more interpretable model. Both have a tuning parameter lambda that we choose by cross-validation. Yeah, mathematically, OLS minimize the RSS, which minimize the same quantity plus lambda sigma beta j square, which you can picture as constraining the coefficients to live inside an R2 ball. The smooth geometrically means coefficient shrinks, but rarely hits 0. You can see it in the figure 6.7. Lasso minimize RSS plus lambda sigma absolute beta 0 is R1 ball has sharp corners aligned to the axis, so the optimum can land on exactly 0 for some coefficients. Hence elections both trade a little bias for lower variance. K-fold. So how can we choose the lambda? So k-fold close validation on the training set picks lambda by minimizing average validation MSE. Yeah, let's move on to the question B. Fit the linear model using with scares on the training set and report the test error obtained. So in code, I initiated a linear regression fit with linear model fit, X train, Y train, and predict with linear model predict X test. I computed MSE linear and RMSE linear and report linear model score for R square. For interpretability, I sorted linear model coefficient by absolute value and tagged coefficients high, medium, low to show which predictor contribute most in magnitude. On the head-out test set, OLS achieves MSE around 1.928705 multiplied by 10 to 6 square, and the root of it, RMSA, 1388.75, and R square is around 0.8575. Interpreting direction at high level, top 10% of high school, and graduation rates are positive, which is academic strengths attracts applicants, and in contrast, yellow is slightly negative. So you can see it on my slide. Let's move on to question C. Fit a rich regression model on the training set with lambda is alpha anyway chosen by close validation. Report the test error obtained. So in code, I defined a grid alpha rich, and I ran the 5-fold cross validation with rich CV. Rich CV in CV is 5, right? You can see. After rich CV fit, I read the optimal alpha is 0.01, and I refitted it on all training data, predict on X test, and compute MSE or MSE and R square exactly as in OLS. And similarly, I did it in Lasso. I set it alpha Lasso numpy log space from 0.001 to 10, and used Lasso CV to pick optimal lambda. Here it is 10, and then I fitted Lasso and predicted on X test and computed MSE, RMSE, and R square, and counted sparsity via numpy sum. Confirming Lasso did not zero any coefficients in this split. So let's see the result. So cross validation selects lambda for 0.01 for rich, which is extremely small. As a result, rich is practically identical to OLS on the test set. MSE is around 1.928705 36 multiplied by 10 to 6 square, and RMSB around 1388.78, and R square is around 0.8575, and all 16 numerical coefficients remain non-zero. Yeah, just slightly shrunken. For Lasso, CV picks lambda 10. Even so, in this data set, Lasso also keeps all 16 coefficients non-zero with MSE around 1.993054817 multiplied by 10 to 6 squared, and our MSV is around 1389.44, and R square is around 0.8574. Yeah, in short, three models deliver nearly indistinguishable predictive accuracy on held out data. So let's move on to question E. Comment on the results obtained. How accurately can we predict the number of college application received? Is there much difference among the test errors resulting from these three approaches? So on this slide, I both explain the summary code and interpret the final comparison across the three models. The code first recomputes each model's R square on the test set and store them as linear R2 and rich R2 and raster R2. It then builds a small dictionary result summary, then lines up each model with its test MSE, test RMSE, and R square, and the number of non-zero coefficients. For OLS and rich, that last field is just the length of the coefficient vector. Yeah, they all use 16 numerical predictors. For Lasso, it uses the sparsity count we computed earlier, non-zero coefficient. Next, the code prints a tidy fixed width table to console with column model MSE or MSV or square non-zero coefficients. So you can see it on the right below. Yeah. So reading that table out loud, linear regression post MSE, MSE or MSE are square with 16 non-zero coefficients, and you can see it rich and raster 2. And what does that mean statistically? First, the R square between 0.857 and 0.858 tells us all three models explain roughly 85.7 to 85.8% of the variation in application counts on held out data. So the basic linear signal is strong. And second, the vanishing MSE differences in Lasso failure to zero any coefficients confirm there wasn't much overfitting for Rich and Lasso to fix with p equals 17 numerical predictors, and n equal NNN 777. Colleges OLS already sits near the bias Variance sweet spot. In other words, regularization did exactly what it should, but it didn't hurt. But there also wasn't much variance to shave off, so all three lands on essentially the same generalization performance. Let's move on to interpretation and practical implication. On R square around 85%, 0.7% means that our predictor explains most of the cross-institution variation in application, but on RMSB is around 1389. About 46% of the mean implies the material absolute error. Expect predictions to be off by roughly 1,000 300 applications. This gap likely reflect driver outside our features, such as reputation and ranking. So we think we need to feature enrichment. So beyond total application, many offices model yields the probability an admitted student allows to guide scholarship and outreach. Data results are broadening to essay text, geospatial context, and fast policy shifts like test optional admissions. More flexible models, ElasticNet, random forest, gradient boosting, and neural nets often boost accuracy by learning interactions and non-linearities, but they demand more data, careful validation, and they reduce interpretability as this system influence aid and assess fairness and governments matter as much as low accuracy. Uh, in this setting, OLS, Lich, and Lasso perform essentially the same MSE 1 point or around 1.993 multiplied by 10 over 6 squared. Our MSE is around 1,389 and R square is around 0.857. Yeah, if your data looks similar, moderate P, ample N, modest collinearity start with OLS. If estimate wobble under correlation turn on leads to stabilize. If you want to parsimony or expect many weak predictors, try Lasso. And in other data set, if we zero the fluff and keep the signal. Whatever you choose, keep cross validation, central interpret RMSE in operation unit, and invest in better feature before escalating to black box model. Yeah. To wrap up, the headline is that simple model go a long way here. Regularization remain a powerful tool, just not always necessary. Yeah. Thank you for attention, and I'm happy to share my knowledge. Yeah.